speak on Sergei Ivanovich's lifetime achievement, the solution of the Bernside problem, together with his teacher Sergei Novikov, and consequences thereof. Bernside problem for periodic groups, as Sergei Ivanovich used to call it, because there are different problems due to Bernside, but this one is the main one. Please.
Okay, thank you, Lev. So, as you said, that's as you said, there's no doubt that this solution of the Bernside problem was the greatest result of Sergei Ivanovich, and he himself says that it is the greatest result. So let me start with a brief introduction. So that's the solution of the Bernside problem was obtained in a joint work by Novikov and Adyanan in 1968, and we know now this result we know is the Novikov-Adyanan theorem. It says that the free Bernside group of exponent n with at least 2 generators is infinite when n is odd number greater or equal than 665. Okay, that's so let me recall that so this we have a the Bernside problem. So the Bernside problem, which was posed in 1902 by Bernside, asks whether this Bernside group is finite when the values of mn are given. So m is the number of generators for this group, and n is the exponent. And of course, it's a non-trivial case when there's a non-trivial case when both numbers are at least 2. So if n equals 1, then we have a trivial group, and if m equals 1, then we have a 1 generated group exponent n, which is just the cyclic group of order n. So that's I have also to recall that the free Bernside group is a free group in the variety of all groups of exponent n. So we have the following presentation. We have this group. We have m generators and all relations of the form x to the n equals 1, where x run over all words actually in the group generator in the generators a1 and 2 and so on. So let me recall what cases are solved. There's no non-solved cases actually, and there are not much. There are not many. We know that on one hand we know that this Bernside group is finite when the exponent is 2, 3, 4, or 6. So that's for 2 or 6 the finiteness of the group is easy. It's just an exercise. For n equals 4, this is the result of SUMIF, and for n equals 6, this is the result of Marshall-Hall from 1958. It's actually that's if you look at this at the list of the results, then you see that the last result, the last positive result was obtained as long ago as 1958. So there's no actual progress for this starting from this year. So there's no progress for several decades. But still we think that there are possible candidates for a positive solution of the problem, and maybe that's possible candidate. One can attempt to prove finiteness of the group for these values for exponents for n equal 5, for n equal 8, and for n equal 12. Okay, that's well. And these are all cases for which we know that the Bernside group is finite. So let's go to the infinite case. So it's as already mentioned that the solution of the Bernside problem was obtained in the joint work by Novikov and Adyanan by the Novikov-Adyanan theorem. So it says that the group is infinite for n starting from, for odd n starting from this number. And okay, that's I always assume that the number of generators here is at least 2. So it's so I always assume this non-trivial case. So no, actually this is the initial joint work by Novikov and Adyanan in 1968. So it was the bound for the odd value exponent, which is 4,381. So that's but okay. Later on, Sergei Ivanovich elaborated an improved version of the proof, and he gave this bound 668. Actually, this proof and some other results which are related to Bernside problem and Bernside groups and some generalization are contained in Adyan's book, The Bernside Problem and Identities in Groups, which was published in 1975. So that's where, of course, there's a simple observation that if you know that the group, the Bernside group is infinite for some value of the exponent, then if you take any multiple of this exponent, then it implies also implies infiniteness of this group because just the first group is the homomorphic image of the second group. So the first is infinite, and the second is infinite. So it's but okay, that's so we have two possible proofs of this. We have a direct proof. So direct proof, which, for example, direct proof that the group is infinite, for example, which is given by the proof of the Novikov theorem, and we have this indirect consequence that the Bernside group for any multiple of the exponent is infinite, but in the latter case, we don't have any structural information. So the first direct proof gives much information about the structure of the group, but in the second case, we know nothing except define the infiniteness. Okay, that's I have to mention also that there was the so-called even case. So that's so I can emphasize that the Novikov Adyan theorem says that the Bernside group is infinite for odd n, and for example, we don't know what happens if the exponent is a 2-power number, and so that's the even case was finally solved by 2 people, by Sergei Ivanov and then by the speaker also, and that's the final result about the even case says that the Bernside group is infinite starting from these values of the exponent. Okay, let me okay, let's before talking about the proof, let me just emphasize that if the best known bound for the exponent for which the Bernside group is infinite, I mean the best known bound, and the known I mean that if there's a full proof of this result and the proof is carefully checked, published and checked, then the bound is still 665, which comes from the book of Adyan, from the current version of the Novikov Adyan theorem. Actually, okay, let's I have to mention about the personal contribution of Sergei Ivanovich to the proof of the Novikov Adyan theorem. Well, it's probably not quite correct to speak about evaluation of such things like a personal contribution in a joint work, but okay, we have a long conversation with Sergei Ivanovich about the history, about the whole process of getting this solution, of getting the proof, and from this long conversation, it is clear to me then that the contribution of Sergei Ivanovich was crucial in this case. I think this is enough to say. Actually, I would like also that the whole process of proving of getting this negative solution of the Bernstein problem took a long 8-year work, starting from 1959. So in 1959, it was a note by Petr Sergeyevich Novikov was published where he described some ideas how to reach the solution. And actually, it took this 8 years before this proof was completed. So it was finally completed in 1968. This is and okay. There was also several years spent on the improvement of the proof. So it's the book by Sergei Ivanovich Adyan was published in 1975. So it's it was like about 5 years to improve this proof, to write an improved version. So let me say now about a few words about the proof of the Novikov-Adyan theorem. So let's, if you just look at the proof, if you as making a glance, then you see just several hundred pages of extremely technical combinatorial arguments. Okay, there. As I said, that there are two versions of the proof. One is just in the original series of paper by Novikov and Adyan, and another one is in the book of Adyan. So this it's they're approximately the same in the volume. And actually, when I'm talking about the proof, I always refer to the improved version of it. So to the version which is which was given in the Adyan's book. So that's and if you look again, if you look at just the proof, then you see that there are about 300 statements proved by simultaneous induction on some non-negative integer parameter, and it's called rank. And if you see the proof a little bit more carefully, so then you can notice that from on the top level, there's a construction of some infinite presentation for the Bernstein group. So that's we have M generators, and of course we have all relations of the form x to the n equals 1. But x, the word x, runs over some I would say graded set of of relations of the form. So that's there are these words x are called elementary periods of rank alpha. So we have the set E alpha, and for each x in this set we have relation x to the n equals 1. They call elementary periods of rank alpha, and this is and we can define a partial group. I mean, the group with just a subset of these relations, and there are just these groups are naturally associated with this infinite presentation. I call this groups level groups of rank alpha. So that's we start from the free group with this empty set of relations. Then we just consider all relations of ranks which do not exceed the given rank alpha. So we just consider this set of relations, and so that's actually that's so this is my personal opinion on the proof. I think the main top level construction is just the main is just we have kind of iterated small constellation. So that's the next level. Each next group is in this sequence satisfies some in some sense a small constellation condition over the previous one. So let me recall what is a small constellation group. We consider just an arbitrary representation for a group, and we consider we consider some sort of set of relators. But of course, we can assume that every relator is represented by a cyclically reduced word in the generators, in the group generators. So that's the letters are the letters which come from generators and the inverses. So it's technically convenient to consider the so-called symmetrized set of relations, so that we just take all relators and take the closure of these relators under all possible cyclic shifts, and then also we take all inverses of the relators. So this is convenient way to consider subwords which are which occur in cyclic shift or relations, or in cyclic shift or relators, or in their inverses. So now let us fix some number in the interval from 0 to 1, and so there's a classical small constellation which has this notation C prime of lambda, and it just says that if you have a common initial segment of two distinct words from this symmetrized set of relators, then this common piece is less than lambda, the lambda's part of each of the relators here. So this is the equality here. And the real small constellation condition, I mean the small constellation condition for which this for which the group is which is non-trivial in the sense that we can say about the group something, is started with lambda equal 1/6 and less. So let's see. For example, I just formulate a simple statement, a simple consequence of the small constellation theory. There are many properties of groups satisfying the small constellation condition, but this is just one of them. And it's as far as I know, it was proved by Greenlinger in 1960. So suppose we have a lambda which is less or equal than 1/6. So that's then the group more precisely then the representation of the group satisfies the so-called dense property, which is as follows. If we have any word which is non-empty, which is freely reduced, and if you assume that this word represents the trivial element of the group, then there is a subword which is also a subword of some relator, and this subword of the relator has length more than one half of this relator. So this property provides a simple, an easy algorithm to solve the word problem in the group. So if we have a non-empty, freely reduced word representing the trivial element of G, then from this theorem it follows that there are more than half of a relator. Then we can easily apply this relator, and we can decrease the length of the word. So that's this is an iterative procedure. So that's if we have this the word which represents the trivial element, that we can make it shorter by applying relations. And if finally if we give it an empty word, then so the word is it represents the word is equal 1 in the group, and otherwise it is not. So this okay. And this condition can be viewed. This condition can be viewed as a small constellation condition of a free group. So it starts with the empty set. We start with the empty set of relators, and we consider this set R. And it can be generalized to this condition can be generalized to a case when we consider a small cancellation condition over some group of it, over a non-free group. So let me consider just example of the classical small cancellation. So let's consider a number p, which is greater or equal than 2. Consider this set U1. So I use this notation because actually this is notation which is used in the Adyana's group. The set of cyclically reduced words in this alphabet, in this group alphabet, satisfying the following condition. So let's consider all. First of all, we consider all non-powers. So this means that any words, a word X that we consider is not a proper power of other word, so this in the terminology of the Novikov-Adyan theory, such words are called minimal periods of rank 1. So okay, I have to say that we consider cyclically reduced words. I mean, this means that we have a freely reduced words which admit no cyclic cancellation. So if for example, if we take any cyclic shift of this word, that it's also freely reduced. And we also consider the condition that x cube has no subwords y to the p, where the length of y is strictly less than the length of x. So why x cube here? Because okay, that's if you consider any periodic word of the form x to the n, and consider another periodic word which occurs in this word, and the period y with period y whose length is strictly less than the length of x, then the length of y is strictly less than two times the length of x. So in this case, y should occur in x cube, and this is y x cube. So if I can put here x to the any power, but x cube here is enough. Okay, that's so let's consider the set of all such words, and it's not difficult. So it's actually an exercise to check that this presentation satisfies the condition C prime lambda as I defined before, with this value of lambda. Lambda is equal p over n. So if n is big and p is not so for example, we can take for p we can take 2, and we have a very strong small cancellation condition, and okay, we have a small cancellation group, and we have this all these consequences of the small cancellation theory. But okay, that's just a very simple first step. And actually, this example shows how to organize a first step in defining this graded presentation for the Bernside group, which I wrote before. So this is namely set 1 for an appropriate choice of this parameter p here. But it represents very lovely, very informally. It represents a general idea how to construct the whole such presentation. So we have a special procedure. So that we have a group on each step, and we consider all elements of the group which are non-powers. And so this is one consider. This is one condition we have to consider, and and also we have cyclically reduced words, and this is but this is these are here in the classical condition. We have cyclically reduced words with respect to free group, and we have to define some notion of cyclically reduced words in over a non-free group which we'll already have over group G alpha, and this so we have a minimal periods of so if we consider G alpha, then then we have minimal periods of the next rank, of rank alpha plus 1. And we also exclude some rods which contains some, in some sense, large periodic rods of the form y to the p. So in some sense, which I do not define here. So this is the general idea how to construct the whole set of relations for the free Bernside group. Actually, it's I have to say that so this is how so for some reason, okay, sorry. This horizontal line here, why I don't know why it appears here. Okay. Sorry. Oh, maybe it's.
It seems perfectly all right. What I see on this.
Okay. Okay. So that's and so that's just as I said. There's a general construction. We start with the free group, and actually, if I wrote the presentation for this group G alpha before, but it's actually it can be written in a slightly different way. So we have a G alpha, and we have this group G alpha minus 1, the previous one, and what happens here? Okay, I do nothing. Okay, and we have this normal closure of words of the form x to the n, where x runs over this set which was called the set of elementary periods of rank alpha. So we have the normal closure of this set, and we have this group G alpha, and this set of relatives should satisfy some sense small compilation condition over this group. So this is this. Okay, this of course I'm not able here to give any details here, and but I have to know that the small cancellation was not formulated in the Novikov-Adyan theory in the Novikov-Adyan theory where how it was presented in the, for example, in the Adyan's book. It was not formulated in some explicit way. It's even if you look carefully at the proof, it is even difficult to extract this condition in some independent way. But the reason is because the very language of the theory essentially depends on the assumption that relations are all periodic with and have large periodicity. So that's very kind of interweaved in the proof in this condition, and there is no. It's difficult to separate this small cancellation condition from in some way because all the language depends on periodicity. Nevertheless, and this is my personal opinion, that this theory can be considered as the first implementation of this iterative small cancellation approach to Bernstein groups. So I think this is a main feature of this, and one of the main features, of course. And as for now, as far as all known proofs of infiniteness of Bernstein groups of sufficiently large exponents are based on some sort of iterative small cancellation theory. So that's I consider this the really pioneering work, and which just shows that this approach works in this case. So it's the very establishment of the fact that this approach really works in this case was a really achievement. And actually, if one tries to realize the approach when this small cancellation approach, and then he or she encounters serious serious difficulties very soon. So that's okay. This is now let me speak about consequences. So that's I classify them as direct consequences and indirect consequences. And actually, this classification is very conventional. It's just what I call direct consequences. It's results that are obtained just applying the original version of the Novikov-Adyan theory. And okay, that's as already mentioned. If you have this theory proves not just infiniteness of the group, but we have a lot of we have many we can obtain many properties of this group which are which come from the technique. So this is just a few results of this search. So it's there's a theorem, and most of the statements of the theorem were obtained in the papers by Novikov and Adyan, and they describe some natural properties of the Bernside group for these values of the exponent. So so we see that the Bernside group has solvable word and conjugacy problem. They are not finally presented. So it was so this is actually this set of relations which are wrote here. So that's the set of relations x to the n equals 1, where x runs over elementary periods. If you filter out some elementary periods in some natural way, then you have an infinite. Then we can get an infinite independent set of relators. This means that neither relator can be deduced from all other one. We have also that we have also that all finite subgroups, all abelian subgroups of the Bernside group are cyclic. So these three statements were obtained in papers by Novikov and Adyan, and later on Adyan proved that the group has exponential growth and is non-amenable. So it's a much stronger statement than just saying infiniteness of the group. Actually, that's the growth of the Bernside group is very close to the growth of the free group. So that's okay. And another application which I could mention, I can mention here. So that's you see. So this is the following theorem. That's for any odd number, for any number which with bound a little bit bigger than this number 665. So this is just a technical thing. That's because for this number we have a little bit more freedom in composing relators and a little bit more freedom in the proof. So for any such number, if you consider the set of periodic relators of this form, that where you see we have this commutator here, commutator of x to the Rn and y to the Rn, and this commutator taken to the power n. So we have the set of relators that we actually obtain an infinite independent set of group identities. So that's, it means that none of the identities is the consequence of the other one. So we have a and this is this gave an explicit solution of the so-called finite basis problem for groups, which and the problem asked whether there exists such an infinite system of independent group identities here. So there was an announcement by so it was solved by Alshansky here, and okay, that's and almost at the same time Adyan gave this explicit set of relators, because Alshansky's proof did not produce any explicit set of group identity of independent group identities here. So this okay, this is another result of this sort. Okay, now I have to say that I just in this talk I realized that I can formulate here only a few of results of this sort which are consequences here. So let me cite another one. So that's another results which I could say that it is of high importance. So that's in operation defined by Adyanan, which is called periodic products of exponent n. So this in the simplest case, this definition is very simple. So consider, assume that we have just arbitrary family of groups, so indexed by some gamma here, and consider again that any odd number which satisfies this inequality, so which is greater or equal than 665. And assume that this simple definition works as when neither of the groups G gamma have an involution here. So suppose all have no involutions, then what we do here is the following: we take the free product of all groups and take the quotient of this free product by the normal closure of some elements of the form x to the n, and x runs over all elements which are not conjugated to some element of the factor. So okay, that's some modern language. It says that we take all non-elliptic elements of the group and say nth powers of these elements and consider the normal group, which is the normal closure of these elements, and consider the corresponding quotient of the product of this. So this operation is called periodic product of exponent n, and it actually solved some equation of Maltsov, which I'm not going to formulate here, but okay, that's it says that it asks about existence of some natural group operation which have certain very natural properties. For example, it is invariant undertaken subgroups and so on. Okay, that's so it solves this question, and if you formulate this natural condition on the operation, that then there were known only two such operations. These are free products and direct products of groups, and this is an example of another one here. So actually, this is just a few of results mentioned here, and if you want to look at more results, and if you want to look at more detailed formulations of the results, then I wrote here several very detailed surveys on the Novikov-Adyanan theorem. So these are quite recent ones. So that's the one in the Russian Mathematical Service and in the Russian journal Успехи математических наук. Another one is труды математического института имени Стеклова. So these are quite large, and these are quite detailed, and also a large part of this service is devoted to say personal attitude of Sergei Ivanovich to to some history related to the results related to the Bernside problem. So, and so I refer the readers. I refer the readers to this two service. And actually, there are more ones, but these are just two most recent ones. Okay, now let's. So let me say a few words about indirect consequences. Again, as I said, I consider only just a conventional thing, and actually it's a difficult question how to. So these consequences are more about not just the direct consequences of not the direct consequences of the Novikov-Adyanan theory, but it just more. They are just more about some kind of influence, and so this again, this is my personal opinion, and I think that the solution of the Bernside problem has a great influence on the results which I list here. So first of all, and the point is that, so for example, even knowing that this approach, this iterative small constellation approach to Bernside groups just works here. It's just an important information. So that's if you know that it works, then you can try to, for example, to do it in a different way. And these are things which many authors actually did. So that's so one of the first consequences of the Novikov-Adyanan theory, of the proof of the Novikov-Adyanan theorem was where other proofs, with appearance of other proofs of the Novikov-Adyanan theorem, and actually again, there was direct proofs, and they give not just infinites of the group, but we have also many properties, many structural properties of the group. Some other properties of Bernside groups were reproved and obtained here. So that's another thing. It's even more. So we this n-periodic quotient construction. So that's okay. That's if you look at the definition of the product. So we have a group, namely we have a free product of some familiar groups, and we impose a set of relations which are out the form x to the n. X to the n equals 1. Actually, if you consider any group and try to we can try to add to the group all relations of the form x to the 1 equals 1, but for n which is sufficiently large, for example, for n which is sufficiently large number. So that's for example, the question is whether the group is finite or infinite, and what are properties of this quotient. So this is what I called n-periodic quotient constructions, and and actually it was realized this construction was implemented, and it was applied to wider classes of groups. So okay, that's okay. That's I do not give details here, but okay, that's the condition which we must have here, like some kind of hyperbolic behavior of the group. For example, if we can apply just to or any hyperbolic groups in the sense of Gromov. So that's beside two things. So these are there were let me cite two results. There were papers by Arshansky here, who in 1980 he gave another proof of the Novikov-Adyanan theorem, which uses a different language, which was more geometric, and which was and the language was use the language of one-campaign diagrams here, and later on, this similar result was obtained for a wider class of hyperbolic groups here. So there's another series of works, I would say. So there is a paper by Gromov Desant and a quite recent paper by Coulon, which I consider as a series because actually Remy Coulon used the same ideas, and that's the same technique as in the paper by Gromov Desant, and that's just you could consider this paper as a more detailed as a more detailed exposition of this Gromov Desant paper, and of course there are some technical differences. But anyway, that's, as I already said, all these papers use a similar idea. We have a construction of iterative small cancellation here, and I would say also that these two papers here, I think that it was the first time this small cancellation condition was formulated in very explicit way. And I think it's a great achievement of these two papers here. Okay, that's but another big activity which appeared after the proof of the Novikov-Adyan theorem, after the original version of Novikov-Adyan theory was appeared. It's they're called it. I would say this is theory of monsters. So there was several examples of groups which with very unusual properties. So okay, that's I think that's my time is almost over here. So that's just if you just look at this at what's written here. So what there are just again I just mentioned here very few examples of such monsters here. Was one, for example, in my list there are so-called Tarski monsters, which are infinite finitely generated groups with all proper subgroups cyclic of some of order which divides some fixed number n. So, for example, if you consider n prime, that all proper subgroups are isomorphic to the same cyclic subgroup of order n here. So these are a series of results here. So these are also examples of groups, of infinite groups with very few conjugacy classes of elements. So almost all elements are conjugate here. So this is also example of so-called Gromov monster, which is a group which does not admit a course embedding into a Hilbert space. And I would like to finish my talk with two questions. One with two problems, and one problem actually is finding a good exposition of the good proof of the Novikov-Adyan theory, which was not so complicated, which avoids unnecessary details, and which is a kind of conceptually simple. So that's and which is also can be applied to rather moderate bounds of the exponents. So that's to my personal opinion, there is no it is still a problem which should be solved here. And another problem is, of course, to find better bounds for for which we can find an approach to Bernside group here, for example, to solve the Bernside problem. So many people, including me, has no doubts that the bound in the Novikov-Adyan theorem could be made significantly less. And actually, there were several announcements of this sort. In particular, Sergei Ivanovich Adyan himself announced that he could prove the Novikov-Adyan theorem for all values starting from 101 here. Okay, but this fork is unfortunately not completed here. It's not completed, so that's just we could consider just this just as an announcement. Okay, so that's I think that's this. I finish.
Thank you very much. Maybe there are some questions in the audience. Yes, in the chat, if you look, here you will see from Sasha Shane.
Sure. So sorry then.
I can read it so far for everybody, and Alexander Shen asks a very speculative question. Is there any hope that somebody would come not just with an improved version, but with an example of a group defined in a geometric or some other non-combinatorial way, for which it is easy to check that the group is infinite and that, say, x to the 11th power equals 1 for every x? Or is there some speculative obstacle for that?
Okay, this I think that's the only now, maybe in the near future, the only way to prove infinites of the group. It's use this idea, this small consolation. I don't think that there's a simple way to prove infinites. So about so that's is this question about finiteness?
No, of course, I should say it should be finitely generated, of course.
Finitely generated, so
what I meant that maybe you can start with some not with the combinatorial representation, but just consider, I don't know, some algebraic construction or group of transformations, yes, or whatever.
But this is exactly what I say. I do not see any other approach. Mm-hmm. So at last, it seems that it's inevitable. I mean, this complicated approach using this combinatorial way of putting relations by portions or by. So I don't see any way.
Okay, thanks.
So in a sense, this is a syntactic or logical approach, one can say. So this is, the objects that one deals here are words, derivations of words, and that's the main realm of what is going on here. So you can use geometric intuitions and tools like Van Kampen diagrams, but these are tools still to get some information about these so logical objects.
Is this a question or?
No, it's just
comment.
It's a comment. It's a comment. It's not a question.
Okay, may I ask a question?
Yes, sure.
The system of relay identities presented on one of your slides, it was written that R runs through all natural numbers.
Yes.
But Adyan book tells that R runs a set of prime numbers. And they both system defines the same varieties, but one system is much larger, cannot be independent. So I think R should be prime.
Maybe, okay, maybe I'm mistaken here. I'm mistaken. Maybe okay, that's probably it should be fixed, and R should be run over all prime numbers. So that's sorry.
And what is your expectation? Would be soon the announcement by somebody of infiniteness of free Bernside group for exponents, say around 50?
Okay, that's I don't think so. 50, okay, 50. 50, okay. I made this announcement.
You may.
I made this announcement.
Why you didn't say today?
But it's a very provisional thing. It's I said that it's still the work is still in progress. So 50, I think it's reachable, and so okay, I'm personally sure that I can do 50, but for in the odd case. But the boundary probably is about 30 or something like this. So that's less than 30. It's problematic.
May I add a word?
Yes, sure.
So the similar estimate is in the work of progress by Agata Atkarskaya, Katrin Tent, and Ilya Rips. So they are doing around 37, something like that. And this is very close, you know, realistic to get this estimate in the near future. That's it. That's just a comment about Rostislav's question.
Yes.
Okay, that's intriguing. So
yeah, okay. That's the point is that the proof here should be carefully checked. It's very easy to make a mistake. I know this by my personal experience. So that's the proof should be carefully written. Okay, the proof should be written, carefully read, and after that we can only say that okay, this was the proof for some bound of the exponent. So I apply here to all announcements of this sort. I apply here to my announcement because okay, I should write the text and then
yeah, makes the question more intriguing than it was. So to say, I would say, yeah. Well, any further questions so far from the audience, or remarks, perhaps? May I venture yet another comment concerning this small constellation property and that you mentioned and emphasized. As far as I remember from the lectures by Sergei Ivanovich, he always told that this idea, on the level of idea, was already present in Novikov's approach. So that's small constellation was already sort of guiding idea that they wanted to achieve. Of course, technically, how to do it is a whole different matter, but indeed, on the level of having this idea that one should iterate and get this small constellation, and then you have this Archon sequence that delivers for you infinitely many elements. That was sort of the source of the original approach. Maybe it was not explicitly in the book, but I would say one should even look in the old, in the papers. Maybe it's even mentioned somehow somewhere in the preface or something. So that's what I wanted to comment. So that was definitely well before the Gromov, Delzant, and Coulomb. So that's for sure. But I mean, I heard this from Adyan, but okay. But this is again.
The real proof, that's the real final proof, was utilize this idea. It's small consideration. But it was just very well hidden in the proof. But okay, that's to me that's absolutely clear that this is a implementation of the small consideration.
Okay, so now actually we should have started our memorial session, but I feel that we need to make a short break. Let's make it 10 minutes before we begin before we start with the memorial session. I'm afraid memorial session probably will be in Russian because too many people want to share their memories. Maybe it's easier to do in the Russian language. Anyway, I would like to thank today's speakers for excellent presentations, for everybody who attended their talks. So in 10 minutes, we will start the memorial meeting. There are a number of people who want to speak there. Thank you very much.